Hi, sirs and madams. Welcome to this little project of ours on automatic slide door system for pantry-type cabinet. Now, I tried to divide this project presentation into 5 sections so it's easy for us to kind of understand and follow along. So, let's see. What does the project try to achieve? If we have like a pantry cabinet like this one, we want to have a sensor, like it's very tiny, it's tiny. It's called strain gauge, or we could have like the full load cell mounted, maybe one at the top here, on in between the door panel and this support frame, right? In between is hidden, so the client doesn't see it. One at the top and another at the bottom. We could have it two, and then the wire runs down. Maybe a slot is made on the back of this door panel, and it goes down, and it's hidden. It's tucked away in the um, toe kick, right? Toe kick area. So we want to have this sensor pick up like touch sensitivity from our client, maybe the doctors, or you know whomever our client is. They can open the door just by touching it. So, and then we'll have our motor mounted maybe at the bottom or the top, hidden enough so it's visually okay for our clients. And then it could slide the door in and out just by our client touching the door, maybe slight pulling it, or slight pushing it. So they don't have to do the manual work of always pushing and pulling. Just touch the door and then it opens, touch it, and then it closes on its own. So hands-free, kind of. You can kick the door even to open and close. So let's look at the electronic circuit setup. So we have 4 major sections or sub-circuit of this. We have the input, which is the strain gauge connected in this bridge form, and it's called Wheatstone bridge. And so the difference in voltage across these two sides, because when deformation happens on the door, on this door, let me say someone touches the door, it creates some strain, some deformation, which is very little on this sensor, this strain gauge sensor, and then it could record this in form of in form of voltage, which is in millivolts. It's very little voltage reading, because it creates like this has coils of wire that forms resistance, and based on deformation the resistance changes a bit. So that's sense millivolts voltage could be amplified and converted to a digital signal for our use in a microcontroller called Arduino. Now, so we have our input, we have our analog to digital converter, we have our microcontroller sub-circuit, and then we have our output sub-circuit for monitoring. So what this ADC, analog to digital converter, does is it converts the signal and it also amplifies it. So we could add more gain to whatever input we're receiving from our load cell, which is combinations of constant time strain gauge, and then you have passive resistors. So like you could have 350 ohm resistors, connected like this in series and all that. So let me don't bore you with this, and then also I added in a serial monitor just to see what's going on when we run the simulation inside of this Arduino microcontroller. And don't mind these LED lights. It's just for visual, and the motor is just for visual to tell us like what happens with the door, because this simulation. And this buzzer plays sound when we're done with calibration. So let's continue. Operation scenarios. We have 4 main operation scenarios. We have automatic operation, to fully open or to fully close without any obstacle. And then we have 2, which is automatic operation to partially close or partially open. And then we have safety stop scenario, in the sense like doing automatic operation when it's opening or closing. If we have like an obstacle in between, because we don't want it to bump on someone while it's opening. So if it's opening, it dictates someone or it dictates an obstacle, it should stop and go back, or it should stop, depending on how we wrote the program. And fourth one is emergency. So we want to allow for manual operation. Someone could, forcefully open or forcefully close it if they want, or if there's power failure, they could, still open the cabinet and all that. So section 4, we're going to look at a brief on Arduino code, and then we want to see okay, let's just head over to Arduino code and see, because we have some functions which are implicitly linked, but they are not recursive. But there's a very important parameter called t that seems to be recursive in our program. So here is the program. You could see we have some global variables, and these variables, we have to change the values for the physical future implementation of the project. Like if we are to physically implement this project, we have to change some of these parameters here. And this is setup function. And then the calibration is called here, to calibrate the sensor, so that we can dictate when it's 1 pound force, 1 pound force, or 2 pound force, based on the human touch on the door. So, and then this is a loop which calls the function we have on this file. So we have, here is a calibration function, for calibrating, and then this is the automation, where the automation functions are. So we have the close door function, which is linked to the open door function, and then you could see the parameter I spoke about, t, which is also calling a function that uses it, and again and again it calls itself again. So it's a little bit recursive. Well, I wouldn't say recursive, it's just being utilized and be called again. So okay, I won't say it's recursive then. So that's what this function does, and then below that, below the automation function, we have some function that check if there's manual force, and there's ones that check if there's positive force or if there's negative force. Like positive force will be when someone pushes the door, negative force will be when someone kind of pulls the door, and no force, like when there's no force at all applied. And then this is a mass function that kind of runs some of our reading up to 2 decimal places. So that's for it for the Arduino code. Now let's head over to simulation. So one more thing I forgot to mention before we head over to the simulation, it's important we know, we understand the minimum positive force, which is 0.3 pound, and also minimum negative force, which is minus 0.3. This is negative force is like when you try to pull on the door, but when you try to push on the door is considered to be positive force. Now we have our manual force, which we set to 5 plus 5 and minus 5, like push and pull, right? So that is the force margin that we've set. So now let's head over to the simulation again and see. Let's head over to the simulation and see what happens. So we make sure that there's no force on the door, right, before we start our simulation, so I can calibrate the system. Now you hear the first beep before calibration, and after calibration here is the second beep. Now you see the red light, it shows that the door is fully closed, and the position of the door t time is 7, right? So, and then if it's fully open, the position of the door is going to be t0. in the sense the cabinet door is fully open. And then if it's closing, it's gonna be yellow. This light LED is gonna be yellow. If it's opening, it's gonna be blue. So now let's try to uh, push on the door. It's closed, right? Okay, let's try to pull on the door to open it. We apply -3 and then -3 and then it starts opening. Okay, and then it gets to 0 and then it stops because it's fully open now. Now we've done fully open. Now let's try to, because the door is open, right? The door is fully open. Now let's assume the client is gonna push on the door to fully close. Now apply some positive force on this load cell or on the strain gauge. Now it's set to close. It's closing. It's closing because we've already applied the force. Now it's closed. It's back to 7, right? And the red light and the close light is red. It's right. Close is red and open is green. So now let's try to run the second scenario, which is we said to be partially open or partially closed. So there could be some times I miss it because of my human error, to partially open, because it's intentional. You want to partially close, partially open or partially close something. It has to be intentional, meaning when the door is closing in, if you want it to partially stop halfway, you could kind of give it a negative pull, and then stop, or put your hand like in between, like to stop it, and then take off your hand. So it takes, the timing is the key factor, like to determine that. But if there is a serious obstacle and then it dictates the obstacle, blocking it, it's gonna slide open all the way again. It's gonna slide open, so it's not gonna stop partially. So it has to be intentional. You have to touch it and then take off your hand. Similarly, like when it's opening, you have to, if you want it to partially stop, you have to touch the door and then take off your hand. Well, if it's sliding open and then it detects an obstacle and the obstacle is not letting go, like the obstacle is still resting on it, it's gonna slide back in. So it has to be intentional. So I'll try to demonstrate that in this simulation, but sometimes I could miss the timing of it because it's simulation and sometimes my human error, like not clicking it properly. Okay, let's try to do it. Now it's fully closed. Let's try to open. It's opening. Let's try to partially stop it by touching it and taking it off hand. Okay, now it thought that we are still resting on it, like we didn't take off our hand. That's why it closed back again, the door. So let's try again. Nice opening. Let's try to stop it and stop it immediately. Now, yeah, we've achieved that. So you could see it's partially open because it's at 4 now, right? The position of the door is at 4. So let's fully open it, and then fully open means we're gonna pull it. So we'll give it some negative force. Let me play a simulation. So we'll give it the negative force. It's opening, right? Now once it's fully open, let's try to do partial close, like it's closing and then it detects a negative kind of obstacle, like maybe a pull on it or something, someone trying to partially stop it while it's closing. So let's try and see what happens. So let's give it the positive push while it's fully open, and then try to, let me be quick, I'm not quick enough, and then yeah, okay, now yeah, we're able to get it. So now you see it's partially closed. It's at 5, T is at 5, and none of the LED lights are on, meaning it's not fully open, it's not fully closed. That is what the second scenario is about. So the second scenario, we wanted to demonstrate like we could program our system to know when the doctor wants the pantry slide door to be partially open or partially closed. Maybe they want to grab something quickly. And then this third scenario, let's look at third scenario, safety. I think we've already demonstrated that. Let's fully open this by putting negative first. It's gonna open fully. Right, let's open it fully. It's fully open. The green light is on. Now let's assume it's closing, right? Let's apply some positive first. It's closing, and then it detects a negative obstacle, and then the obstacle doesn't want to leave. Now you see it starts sliding out because the obstacle is not leaving. That is safety. So again, also like let's try when it's opening. Let's close the door and then let's see when it's opening. We're closing it. It's closing. It's closing. Let's fully close it, and then we're gonna try to open it. Okay, let's pull on the door, trying to open it. Now let's assume an obstacle just comes in to stop it. A positive obstacle. It starts closing immediately because not immediately, but after some delay, because you notice the obstacle is not letting go. So that is safety scenario. Now the last scenario is emergency. So we want like let's go back to the simulation. We want above a certain force, and that force we call it manual force, which is 5 plus 5 or minus 5. That is pull of minus 5 pound force. So above this or below this, we want it to be considered as manual operation. The client is forcefully wanting to open it. It's not intentionally wanting the automatic system to do its thing. So let's run that scenario and see what happens. So let's assume it for pull. Now it's fully closed, right? Let's try to open the door, and then we're gonna go beyond that. We're gonna go all the way to minus 5, and then you see immediately we'll go beyond minus 5. Even if, let me pause the simulation so we'll see what happened in the console. Now the door was still opening, right? Because we pulled it, it was still opening, but immediately it takes like the force pulling it is so great, it just overrides the motor and it stops the automatic system, and then the manual system kicks in. So you see it writes manual operation, it's writing, repeating the force, the amount of pound is coming from manual operation. So because it dictates like the client is just wanting to force it open. Maybe it's in a hurry, he wants to just open it quickly and grab something manually, forcefully trying to do that. Now, similarly, we could see for let's put it back to neutral to 0. Let me run the simulation, put it back to 0. Now, similarly, let's see it's back to is continuing the opening operation because we didn't physically manually pull it open, so because it's simulation. Now let's try to see what happened if the clients want to forcefully close it. So we're gonna go past to positive 5. Let's see, positive 5. Ignore the automatic system. Once it dictates that force, right, it's gonna override the automatics, and then you're gonna be writing let me pause the simulation. It's gonna be writing manual operation, because the force is greater than 5 pounds. So this is a demonstration of these scenarios, and this is mostly simulation. I know there's more challenges like in the future to try to implement this in physical in the physical model, like to have it physically. But I feel based on how much I've been able to accomplish, I've been able to accomplish both in the code and in the electronics. I feel it is gonna shorten that time. It's gonna reduce the challenge a lot. So mostly what we might have to tackle in the future would be to calibrate some of our initializing parameters, so to properly calibrate it. Because in this case we just have like a simple load cell, just one load cell, and then the reading is just it's just very noise free. It doesn't have much noise. It's just, incrementally going up and down. But in a physical model, when we have the pantry door, we'll face more challenge because the sensor within could be tricky because of noise and different things. Like, you need to properly filter the reading. So, well, it's highly possible through God's strength and through God's grace. I feel we could achieve it. The automatic door system for MCC. So we don't have to rely on the manual toe kick. I feel this is way better. Like, for future, it's a bit future proof, because once our clients find out that it's really handy and helpful, it will boost our company's reputation in terms of advanced cabinetry. So thank you, sirs and madams, for taking your time to um, hear my little presentation. So God bless you all and see you around. Bye bye.